Hey everybody. Oh, and I guess I didn't ask you about sound check, but I'm good. Okay. Hey, let's talk about today's lab. It's a pretty involved lab. It's going to take both of us really to do a lot of work. Again, we're working as partners. I'll keep saying that. It's called static equilibrium. It is our way of introducing you to torque. Hopefully you already saw the lecture there on chapter 9 and all those fun calculations with torque and the concept of torque and the two conditions of static equilibrium. And that's where I want to start. Let's do a quick review of the concept. If I took an object, and our object is, we'll just call it a rectangle, because you'll see that kind of matches our equipment really well. And so if I just make a rectangle and apply some forces to it. So let's say that right here I apply a force, call it F1. And then maybe right here I'll apply a force of F2. And those by itself kind of looks like, and I'll call this the center, kind of looks like maybe they're a little competitive in terms of rotation. Maybe this one looks a little stronger. It kind of depends how big that force is. But it also kind of looks like it's being pulled down this way. And so, let's see, if I've got one going this way, I guess it would be nice to have maybe another force, maybe this way. And so I'm just obviously making these up. I'm not sure if those will come into equilibrium. But it's maybe kind of looking that way because, again, it looks like these two are kind of pulling it this way. This one pulls it that way. In terms of rotation, this one looks like it's rotating this direction. This one looks like it's rotating this direction. But it looks like that one might be a little more torque, so I'm going to give that one. So, again, I will say that these may not be the perfect match. That's not what I'm after. What I'm after then is our two conditions of equilibrium. Remember, the first one said that all the forces have to add up to 0. Now, of course, really what that means is all the forces in the x direction have to add to 0, and also all the forces in the y direction. And if you remember from the lecture, we said, well, of course they do, because if they didn't, it would have an acceleration and it would move. So here's what we're going to do. We're going to hook up a bunch of forces. We're going to get it hooked into equilibrium, and once it's in equilibrium, we're going to test this theory. We're going to say, is this true? And so as we work as partners, I'll be your hands in the lab, and so I'm going to take a rectangular object. I'm going to apply a bunch of forces to it until I get it balanced. And then I will send that data to you. And what you're going to do then is to look at the x and y component and go, okay, are they balanced? And hopefully, when you add yours up, you will get something close to 0. All right. Really, all I will ask of you in the lab is you add up all of them in the x direction and see what you get. But I know from experience that you will get something close to 0. Not exactly 0, because as you'll see on our equipment, I'm going to hook this up, but this little platform has to rest on some ball bearings, and therefore there is some, but minimal amount of friction, and that's why they won't come out to be exactly 0. They'll actually add up to the amount of friction in the ball bearings, because we know in theory they're supposed to come out to be exactly 0. So what we're going to do our best to make sure that this plate here is sitting down. In fact, maybe I'll just take a moment to show you the plate. It's going to look like this. It's got this metal plate right here, but on the front of it I'm going to put a rectangular piece of paper. Okay, and what then I'm going to do is put on a table, and I'm just going to put some ball bearings on the table. Oh, and I didn't level this one. Let's see if these ball bearings stay. Oh, good, they do. Just going to put some ball bearings on the table, and then I'm going to put this heavy metal disc with kind of a rectangular surface on it right here, and then I'm going to hook up a bunch of forces. And the way I'm going to hook up the forces is just take some of this string. This stuff's all in a knot. Here's a decent string. And I'm going to connect it here and put a pulley here and then just hang some weights. In fact, maybe I'll roughly show you one of the pegs. They go into the table. Maybe best if I take it off the ball bearings, and maybe you can even see it better if I kind of have it here. But we've got these little peg holes, and I just like to put the graph paper on there and pinch it and go, okay, there it is. And then that way I can then take some string, make a little loop, and loop it over there. And then of course, if this is sitting up on our experimental table, this, I can then put a little pulley under here, and on this end of it, hang some weight. Now in this case, if I hang just one weight, it's not going to be in equilibrium, it's going to go falling off. So let me just grab it here and kind of show you by hooking one weight on here. And so there is how I'm going to attach a tug, a pull. Okay, and we're asked to do this 2 times. The first time we're asked to hook up 3 forces, so that's where I kind of started this conversation, hooking up 3 forces. Then you're asked to do it a second time with 4 forces, but each time, and let me just disconnect this for a second so I can talk to you. Okay, don't fall. So each time what I can do then, or actually what you're going to do, because remember, we're working as a team here. I'm going to do the parts that need in the lab, hands-on, hooking it all up, and then I'll give you an opportunity to write down the data and then do the calculations. So if I hook this up right, it will be balanced, and what I will do is I will write down the values of F1, F2, and F3. And then of course what you're going to do is to see, do the forces in the x direction come out to be 0? Now, maybe in a different color so it stands out, you'll notice that I am hooking these forces up on a grid paper. And so, oh, green not stand out very well? Ron says use blue, okay. So I'm going to just put some lines in here, because what you're going to get is a piece of paper after we work on this together. You're watching the video and I hook it up. What you're going to get is this piece of paper that has values for the 3 forces, and they have lines on them, and you're going to have to measure the angle in order to figure out what is the x component and what is the y component. Which is why I took a moment to print a protractor. Now, we have some really good protractors here in the lab, but I know at home you might not have a protractor. So hopefully you can have access to a printer, because this one is going to involve some printing so we can do some actual hard measurements. And so like I said, you're going to get this piece of paper scanned, and that's going to be needed to be printed, so that then if you just go to Google and click on image and go protractor, they have a lot of printable protractors online. And so I just, right before I came in here, I go, hey, let me print one up so that I can show the students what I'm talking about here. All right, so you'll need a protractor. All right, so taking that protractor, you're going to measure your angles, and you can measure whichever angle you kind of choose. But let's say for force number 1, I measure this angle, so I'll call it theta 1. Let's say for force number 2, I measure this angle, theta 2. Let's say for number 3, I measure this angle, theta 3. And even though this is a review, since we've been doing forces, and we really want to get into torques for this lab, let me at least help demonstrate how I would do the mathematics. So to get the x component, I would take the force of number 1, multiply it by cosine of theta 1, right? Adjacent, okay? And notice positive. And so there would be the x component of number 1. And then the y component of number 1 would be F1 sine theta 1, and it's down. And so force number 1 is to the right and down. So to the right, the x is positive, and down means the y is negative. So that would be the first 2 terms that would go into this calculation that you're going to do. Now, the second force, so I'll look at the second force. Notice it is to the left and down. The left means negative x, and the down means negative y. So I'll just come over here and put a negative for each of them. Negative, negative. For the x component, it would be the F2 adjacent cosine theta 2. And this would be F2 sine theta 2. Okay? Now, maybe I should just also give a little warning here. It just kind of dawned on me that some of you might just want, just go directly plug and chug into that equation. What I'm drawing on this picture up here is not what you're going to get. You're going to get something that we're going to hook up and measure here. And so what you call theta 1 may not match this. Okay? So you've got to come up with this formula on your own. So please don't just do a direct plug and chug. Do this. Add up all the forces in the x direction. And so you got to figure what they're out. Okay? Well, let me keep going. Let me go to force number 3. So force number 3 looks like it's up and left. So the up part would mean a plus for the y direction. The left part would be a negative for the x. And then this, of course, would be F3. And coming to my picture, I would want, for the x component, the opposite of number 3. So this would be sine number 3. And just let me say it again. Whether you use sine or cosine here really depends on how you set up your angles and how you measure them. So don't copy this formula directly. What you want to do is just add up the x components. Okay? And then, of course, the up part here would be F3, and then this would be cosine. And, of course, maybe this is worth making a comment. We've done this for the last few chapters. I know this is summer school, so it's going kind of fast, but hopefully it's beginning to sink in that you don't always use sine for the y and cosine for the x. You do, of course, do that when you measure your angles from your x-axis, which I have done that for number 1 and number 2. But for number 3, I went ahead and I measured from the relative to the vertical axis, and because of that, the roles switched. sine and cosine. Again, that's why it's always better to think about cosine as adjacent, not x, and sine as opposite, not necessarily y. Anyways, as we hook these up, this will be your first set of calculations. You will then take the data that I'm about to help you measure, and you will then pick an angle, any one you want. I mean, some people will measure from the vertical and some people will measure from the horizontal. That's fine. But what you need to do is add these up and see what they come out to. And I will tell you that they will come out to be a pretty small number. Remember, they're supposed to come out to be 0. Now, they'd come out to be a small number if there are other forces, and the ball bearings under here are pretty good, but like I said, they have some friction. And so I'm going to ask you to just see what it comes out to be and record that down. Now, here's where it gets, I think, funner, is where then you're asked to do the torques. This is the equilibrium number 2, or condition number 2. Because condition number 2 says the sum of the torques should come out to be 0. And so in mine, let me show you the torques. Maybe it's worth putting here what we just saw in lecture, that the torque would be R perpendicular times F. And so you're going to need a ruler also. Now, what I liked about this protractor is, in addition to having an angle, it also had a ruler down here. So that's the reason I picked this one, is I could just print this and cut it out, and it would work as both a protractor and as a ruler. But rulers are much more common, so I have a suspicion that you guys probably have a ruler at home somewhere. All right, so a protractor and a ruler, because you need to measure now some distances. But you also need to draw some straight lines. So you need a straight edge. That doesn't have to be a ruler. That could just be an edge of a piece of paper. But again, if you have a ruler, that would be best. Because what I'll do, maybe I'll switch to an orange color here, is let me work with torque number 1. So torque number 1 is really, if you making a line that extends. Remember that I said in lecture, the line of action, just kind of extend out the force somewhere. And then kind of using my protractor, and in fact, since I didn't cut mine out, let me grab let me grab a good protractor. All right, I'm back. Looks like the fastest one I found was a full protractor, hole 360. So as you know, most of them, and the one you're probably going to print is a half circle. Okay, but I found this right away, so I'll just grab that one. But what I like to do with the protractor and then the ruler is to lay it up here so I can accurately measure the perpendicular distance. And so, be something, something like that. But again, to measure that torque, you've got to get the perpendicular distance. Let me actually then just put R perpendicular 1. And so to actually go ahead and calculate the torque, I can put in my number for the perpendicular distance. So I'll go R perpendicular 1 times force 1. Now don't forget there's pluses and minuses, so which way is this rotating it? Now you'll notice I picked the center of it, and that's what I want to talk about for a moment. So I'm thinking about, okay, how would this rotate around its center? And so you gotta have to apply a little bit of physical picture here. Maybe you could even just imagine putting your finger on it and pulling it this way. That would tend to rotate it in a clockwise direction. Traditionally, clockwise is a negative rotation. So I would say the torque I'm getting from number 1 is a negative. And so there is how I'd calculate the first torque. Okay? So perpendicular distance and force, and like I said, that's really the main part of this chapter because you've already been introduced to forces, but it's torques that are a little harder. And we're trying to see that something in equilibrium, the net force and the net torques would come out to be 0. All right, let me also demonstrate with number 2. So here's number 2. Again, I probably would take my ruler and make a line of action. And so I'll extend the line of action to here. Then by using my protractor and my ruler, I would measure the perpendicular distance. So let me call that R perpendicular 2. So in my calculation, I would come over here and say, let's take R perpendicular 2 times F number 2. And so that would be the torque. Now, whether it's positive or negative, let me think about the rotation here. And so again, maybe you can kind of imagine putting your finger here and then pulling on it. Looks like that would rotate it in a counterclockwise. And it looks like it would be kind of difficult to get it to rotate because we don't have much of a lever arm here. And so technically this would be a positive torque, so I'll put a positive. But if I had some real numbers in here, that would probably be a small amount of torque. Okay? Well, then finally, showing you in my picture, the last one, number 3, would look something like this. I would take the line of action, so dot, 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 dot. Using my protractor to make sure that I'm measuring perpendicular. I guess I would have something right about here. And so that would be R perpendicular number 3. And so to calculate that torque, I would come over here and say, okay, it should be R perpendicular 3 times F3. And then, of course, that question about positive or negative. And so you kind of maybe have to imagine. And for me, it works easier if I just kind of actually put my finger on the piece of paper and then kind of tug here. So I kind of tug. And you can kind of see that that would rotate it in a counterclockwise direction. So that's a positive. And it's got a small r, so that's positive. And actually that makes me feel kind of good. I had a big negative and 2 small positives, and the whole point is they should add up to 0. And so let's see what you get, okay? And so I'll say it again, even though I haven't actually done the balancing act yet and I haven't given you any data, that's going to be included with this email. But your job is to run through these calculations. And one more. Here's a fun piece. When you get this far and you get that the sum of the torques is 0, or I probably should say near 0, you are hopefully convinced, yeah, look, the forces in the x come out to be 0 or near 0. The forces in the y come out to be 0 or near 0. And yeah, the torques come out to be 0. And those are torques measured from the center. So that means it doesn't rotate around the center. But something in equilibrium, I would say it is not only not rotating around the center. So there's a double negative. Let me say it again. It is not only not rotating around the center, but I would say it is not rotating around any point. And so your author's kind of clever here. Your author says, after you do these, on step 4, he says, do another torque calculation. Pick any place you want, and that too should come out to be 0. Because the truth is, it is not rotating around every point. So the torque should come out to be 0, not just the center, which I think is what most people kind of gravitate towards. You'll see in my equipment, I have a center hole, and so it kind of makes sense to do a calculation around the center, because you're like, well, yeah, it can twist and rotate around its center, sure. But the reality is, it's not twisting and rotating around any other point. So, to kind of have more experience calculating torque, your author says, go ahead and calculate a torque around a second axis. Any one you want. All right. So I'll tell you what. I'll do the corner of the paper. All right. So maybe to make it stand out, I will put a big green dot, so you can see it, down in the lower right-hand corner. But please know you can pick any place you want, okay? But let's try it again. I would even encourage you, since I'm going to send you a picture of the data we're about to collect, you'll have so much on this by now, you might want to print this twice so that the second torque calculation we won't confuse with all the other stuff here. Let's see if I can draw it up here, and I know green doesn't stand out as well, but I don't want you to confuse it with my orange. See, my orange was the perpendicular distances, when I measured it from the center. The good thing about it is I don't have to draw lines of actions again, right? The line of action is the same, and I just got to figure out what the perpendicular distance is. Now, I just realized that, unfortunately, my line of action of number 2 would actually be off the piece of paper. So, but not by much, so I think you'd be okay to measure that one. Maybe you can put another piece of paper underneath it, so you've got kind of an extended piece of paper. Or maybe you want to pick a different point than the edge of the paper. That's the consequence of me picking the edge of the paper. But to illustrate it then, I would call this perpendicular distance 2 and label it in green. Let's see. Line of action of number 1 is here. Using my ruler and protractor, I would get a perpendicular distance, R perpendicular 1 in the green. Force number 3, again, I have a line of action, and it looks like if I do a perpendicular distance right here, I would get R perpendicular 3. And so notice I have very different R's. But yet, the torque should come out to be 0. So, let's see what happens here. So, I'll do the first torque, and I guess I'll do it in green to kind of keep with that theme. This would be R perpendicular 1 times force 1. Let's take a look at it. This is R perpendicular 1. This is the force. Again, if you can kind of imagine putting your finger here in the corner of your paper and tugging on it. that would make it go in a clockwise direction. And so I'm going to put a little negative in front. So that's a negative torque. So the first one's a negative. It could have changed depending on what point I picked, but I did get a negative here. Now, let's go on to number 2. Number 2 would be this perpendicular distance and then this force. So it would be R perpendicular 2 times F2. And let's look at the direction of rotation. So if I tug on it here, again, that's going to make it want to go in a clockwise direction. So that's a negative. Did you notice how the sign of the torque changed, right? See, that's what I was saying. You do this from a different perspective, a different point, it may change the sign from positive to negative, whether it makes it rotate clockwise or counterclockwise, right? In other words, if I had a force going down right here, and I was thinking of this as the rotating point, that would make it go like this. But if I was thinking of this as the rotational point, that would make it go the other way. So in one case I get a negative, in the other case I get a positive, or from my perspective. From your perspective, I guess you'd call that negative and this positive. Okay. So that's, I think, a neat added benefit of the lab here is to kind of illustrate, hey, torque is more complicated than force. Torque actually can change from positive to negative just because we change where we're talking about calculating the torque. And that didn't happen with forces. No matter what you think about the force, if the force is down, it's down. Stand on the other side of the room, it's still down. Go to the other side of the room, it's still down. It doesn't change direction, but the torque is relative to some pivot point. And so it depends on what side of the pivot point is that force. And so I wanted to illustrate that. And then again, that's why I think the author took the time to say, do it a second time. Make yourself realize that the torque should be 0, not just around the center, but every point. And look how the math plays out. It's very interesting and more complex. And that's why I keep spending more time with torque, because I know students always have struggled more with torque than forces. Forces were hard enough, but torques are even harder. All right, so let's move on to the third torque. All right, so the third torque, of course, would be this line of action. So I would call this R perpendicular 3, and then force 3. And to decide whether it's positive or negative, I might imagine my finger holding the pivot point and force number 3 tugging it like this. All that looks like it's going to make it go in a counterclockwise direction, and so that's a positive. And that's good, because I was getting nervous, because obviously if this has to come out to be 0, if all 3 were negative or if all 3 were positive, you're not going to get a 0. You got to have some variation in the sign, and at least, two, like this is 2 negatives and a positive, or you can have 1 negative and 2 positives, but to get 0, you've got to have some pluses and minuses in there. All right, so again, hopefully that's what it comes out. Now, I'll say it again. This is a big lab because both of us have a lot of work to do. I have to hook this all up. You have to do all these calculations. And of course, that's what you're going to do. So that kind of set it up. Now, here's the second half of the lab. The second half of the lab is really just like the first one. Let me come over here and draw a picture. And I won't even bother to go in too much of the detail. I'm just going to put on this piece of paper 4 forces. And then I'm just going to put same. In other words, what I'm going to do is balance a rectangular object with 4 forces, and I'm going to record down their direction and their magnitude. And what you're going to do is you're going to add up the components in the x direction, add up the components of the force in the y direction to see if they come out to be 0. You're then going to calculate the torque around the center, but then some other point, and maybe the corner of the paper, wherever you want. but you're going to calculate the torque another point. So you got to do all of these calculations a second time for the other balanced object. All right? So just to make it clear, and what you're going to turn in is you are going to turn in a set of 4 calculations twice. Right? These 4 calculations when we balance it with 3 forces, and these 4 calculations when we balance it with 4 forces. Okay? That's what you'll be turning in. Now also, you might want to turn in your piece of paper here that had all your little drawings here. So I would say you might put all your calculations on one piece of paper, but you should have this looking thing and then calculations, and you should have an identical looking thing for 4 forces with these 4 calculations. All right, now to the hard part of the lab. I got to balance it for you, right? I got to then actually hook this up, get it balanced, and so we can actually mark it on our graph paper. Because like I said, if I came over here and hooked up just one force, that would not balance it. I need to hook up a second and a third and get all this to balance. Once I get it to balance, because that's my job, my job is to be your hands in here, then we're ready to go. Here's some good news in terms of time-wise. I already did it before I started the video camera. And they're right over here. Watch. I'm going to come over here, and I'm going to look here at this one. And Ron, if you can kind of maybe, I don't know if you want to zoom in, but I also want them to see the weights that are hanging here. I have 3 strings connected to little pegs that are then hanging from this table with some weights off to the side. And so what I need to do, and I'll mark these with a little more accuracy off camera, but what I'm going to do is take this and put a little mark right here. So that when I take this apart, I can draw the direction of this force. And so this will be force number 1. And also, so I can give you some numbers here, I'm going to just look at the weight. It looks like I have 250 grams hanging from it. So I'm also going to write underneath it here 250. So I know that I have a force coming this way that I'll change to kilograms and then multiply by 9.8 and get newtons, and I'll write that on there too, but I'll have a direction. So I'll have a direction and a force. Well, let's call this one number 2. It looks like it hangs down over here. And so if I mark it right about here, and then read the number, it looks like I've got a 200 and the hanger, so I got another 250 this way. When I take this all apart, then I can make it look a little nicer. I'll put a full arrowhead across. I'll go ahead and then, actually calculate the force in newtons and write that on there. And so you'll have an arrow with how much force, call it number 2, and over here. In fact, so I remember when I take it all apart, I'll put a number 1, and I'm calling this one number 2. Okay, and then the third one is right here. It's coming over down this pulley. It looks like it comes off right about here, so I'll make a little mark. And so I can draw that better for you when I take it all apart. Let's see, I have a 50 and another 50, so that's 100 grams hanging there. So I'm going to write here maybe something more, a little solid, 100 grams. Put a number 3 by it. So it's this piece of paper that I'll scan. I'll make it look a little nicer also first, but I'll scan it, and that's what I'll include. And then that's what you need to do is these 4 calculations using these 3 forces. Now that I measured them, I can kind of mess them up, and I think you can see it a little better if I mess it up. See if I like tug on this a little bit, it, you know, makes it rotate, or if I push it, oh, now I really messed it up. And so I knocked it out of equilibrium. And so you could imagine that these forces and angles have to be just right. And that's why I said we both have a lot of work, and I didn't want you to have to watch me for 15 minutes, keep playing with the weights and the angle to get it balanced. That would be unnecessary. Our time would be more valuable putting it up there. So I thought, okay, why don't I just kind of hook that up? All right, I also hooked up an identical one with 4 forces. That's over here. Come over here, Ron, and we'll look at this crazy one also. So this crazy one, and I don't know if the students can see. Can you see I've got 2 weights hanging here, and kind of on this back side there's 2 more. You can see the 4 strings. There's 1 string, I'll call this number 1, I'll call this one over here number 2, I'll call this one coming towards you number 3, and this one kind of going back, and you might not be able to see it, goes back towards this monitor, so that's number 4, okay? And again, it's all balanced. Let me not touch it until the end to show you that, you know, what this thing looks like, but it's got that disc right here, and see I can kind of wiggle it a little bit. And if these forces and torques were not balanced, this whole disc would go sliding all over the place. Okay, and of course I have this little center peg here, so I can just kind of check, is it got a little space between them? Yeah, it looks like it does. Looks like I'm pulling. So let's go ahead and mark these. Let's see, I'll put right here a little mark. For direction. And so when I'm done here, I can get a good line for the direction. And the magnitude, it looks like I've got 150. So I'll put here 150 grams before I take this all apart. What I called number 2 is over here, and so I'll make a little mark parallel to the string. And it looks like I'm hanging 150 also. Is this one balanced? Make sure it's not touching. Yeah, I think, all right. I think that's good. Let me just check. Good. Not touching. Okay. Oh shoot, now I messed up the angles a little bit. Try to put it back where it was. Okay. I called this one number 3, so let me make a mark kind of parallel to the string. And get a number, and it looks like I'm hanging at 250. And finally, the last one over here would also be 250. I'll call that number 4. You know, I'm a little nervous about it. I kept bumping it around so much. But I think I got the right measurements before I kind of adjusted everything. So we're close. Hopefully we're still close enough that when you add these up, they come out to be 0 for those. All right. Now, again, I'll show you, like if I were to take this off and mess with the weights somehow, maybe I'll just take this one off. You'll watch. Whoa. See, it's no longer in equilibrium. And so this is the part I was showing you. This is this crazy metal disc that fortunately did not crash on my toes, but here it is with all these ball bearings underneath there, so it can roll around. And that's, like I said, why I needed about 15 minutes to kind of keep playing with the weights and changing the angle to get it all balanced. And so it took me, actually I kind of did this one faster than I thought, so that was about 10 minutes, the other one 15 minutes, and there was no point in you watching me balance. But I did want you to see me unbalance it so you can see how it falls apart. So one last time, I did the hands-on stuff, and I'm going to send you then the measurements that have the direction and the force, and what you need to do is then draw on these with their angle and the perpendicular distances, so that then you can do the 4 calculations for each of them. All right. Hopefully you'll learn a lot about torques in this lab. Take care.